Let's talk about the very fabric of reality. You and I, we experience the world as this perfectly smooth, continuous thing, right? But what if that's just a grand illusion? What if, when you zoom all the way down to the smallest possible scale, the universe is actually, well, pixelated? For the longest time, physics has treated spacetime as this beautiful, continuous, flowing fabric. But a really radical new idea is starting to challenge that entire picture. It's suggesting that reality is actually built from tiny, discrete, indivisible units. So, which one is it? Okay, so this slide lays it all out perfectly. On one side, you got the standard view we all know, smooth space-time where a wave's wavelength is just a basic fact about it. But on the other side, we have this wild new idea from physicists Jonathan Oppenheim and Sun-Hin Hong. Let's just call it the JSH theory for short. And it pretty much flips everything on its head. It says no, space-time is pixelated. Wavelength isn't fundamental, it's something that emerges. And the speed of light? That's not just some random constant, it's baked into the very structure of the universe. To really get how radical this new idea is, let's just do a quick refresher on the classical picture. How do we usually think about waves moving through space? So in the standard model, you can think of spacetime as a passive backdrop. It's the stage, and the waves are the actors. A wave's wavelength is just part of its costume, a property it brings with it from the start. The stage itself has nothing to do with creating it. All right, now let's leave that nice, smooth stage behind and step into a much weirder, grainier reality. Let's talk about these hidden pixels of space-time. The core of the JSH framework is that space-time is made of these fundamental building blocks, kind of like pixels on a screen. You can't get any smaller. And what this means is that a wave can't just travel in a perfectly smooth straight line anymore. Instead, it has to literally hop from the edge of one pixel to the next, navigating this underlying grid of reality. So you're probably wondering, if everything is just hopping from pixel to pixel, where the heck does something like a wavelength even come from? Well, this is the most brilliant and kind of counterintuitive part of the whole theory. It's not about the wave itself, it's all about the journey it takes. It all comes down to this idea called path complexity. Because a wave can't just cut across the pixels, it's forced to take all these tiny detours. Think about it like a taxi in Manhattan. It can't just drive diagonally through buildings to get from point A to point B. It has to follow the grid of streets, right? So its actual path is way longer than the as the crow flies distance. And that inflation of the path is what actually creates the wavelength we see. So in a smooth universe, the path from A to B is a simple straight line, the shortest possible route. But in a discrete universe, it's a constant zigzag. The wave has to navigate around these fundamental voids in the grid, which means it takes way more steps to cover the same distance. The key takeaway is simple. The path itself gets a whole lot longer. Now, I know what you might be thinking. Doesn't this mess with Einstein's whole speed of light is constant thing? And the amazing answer is nope. The fundamental speed of the wave, the speed of each individual hop, is still the good old speed of light. What changes is the effective wavelength we observe from afar, and that's a direct result of how complex its journey was. The more complex and detour-filled the path, the shorter its effective wavelength appears to be. And one of the authors, Sun-Hin Hong, really nailed it with this quote. He says, "Wavelength modulation arises from path complexity, not from altered dynamics." In other words, this isn't about changing the laws of motion. It's a purely geometric effect. The very shape of space-time itself is creating the properties that we observe. Okay, this is a mind-bending idea for sure. But is it just a beautiful piece of math? Or can we actually find evidence for it out there in the real universe? Well, to find out, we have to look at the most extreme places imaginable, black holes. I mean, think about it. If you wanted to find a place where space-time is so stressed, so warped, that it might actually reveal its underlying pixelated nature, where would you look? You'd go to the most massive, most gravitationally intense objects we know of. And check this out. Here on Earth, this path complexity effect is basically zero, totally negligible. But look what happens when you get near a neutron star, or even better, the edge of a black hole. Suddenly, this new effect becomes just as strong as the gravitational redshift predicted by Einstein's general relativity. It becomes a real signal that we could actually hope to detect. And the absolute perfect place to look for that signal is in the aftermath of a black hole merger. See, when two black holes collide and merge, the new, bigger black hole wobbles for a bit, like a bell that's just been struck. And those vibrations, which ripple outwards as gravitational waves, are called the ringdown. They carry this incredibly pure message about the nature of space-time right at the black hole's edge. And here's the most exciting part of this whole thing. This isn't just science fiction or some philosophical idea. This theory is so well defined that it makes a concrete, testable prediction that we can check with data we already have. So, the whole test boils down to measuring one single number. It's called eta. You can think of it as a reality check parameter. It's just a simple ratio comparing the speed of light in this new pixelated theory to the speed of light in general relativity. Are they identical, or is there a tiny difference? Now, general relativity makes a very clear, very simple prediction. Eta has to be exactly 1, period. No deviation, no wiggle room. So that's our baseline. Any measurement that shows eta is not 1 would be a huge sign of new physics. But here's the theory's smoking gun. It doesn't just predict some difference. It predicts a very specific, rigid signature. It says that if eta isn't 1, then the ring-down frequency has to go up by eta cubed, and at the same time, the time it takes for that ring-down to fade away has to go down by eta cubed. This perfect anti-correlation is what makes the theory so powerful and, maybe more importantly, so easy to prove wrong if it isn't true. So the billion-dollar question: what do the actual observations from our incredible gravitational wave detectors, like LIGO, Virgo, and Kagra, actually say? Did they find anything? And here's the answer. The data we have today has already put this idea to the test, and what it shows is that if there is any deviation from general relativity, it has to be less than about 2%. Now, that is incredible. We haven't proven the theory, right? But we've shown that it's consistent with what we see, and we've massively narrowed down the space where any new physics could be hiding. And that's the real beauty of this. This isn't some untestable fantasy. The source material for this whole explainer actually provides the Python code to run this test yourself. It uses publicly available data. This is real, verifiable science happening right now, pushing at the absolute boundaries of what we know about the universe. Which brings us to our final thought. We've just looked at a concrete, testable theory that suggests the smooth reality we all experience might just be an illusion, built on a hidden, pixelated grid. And it forces us to ask, if space-time has this hidden texture that we're only just now beginning to probe, what other fundamental secrets might it be hiding from us in plain sight?